Good afternoon, everybody. I hope you've enjoyed your coffee. It's my great pleasure to represent Team SKIM, which includes industry, it includes scientists, and it includes engineers. All the people who have worked on SKIM have been working towards this presentation in a certain way, which is to try to give you an idea and a representation of the performance of the mission that you've seen presented earlier. What we're trying to do in this presentation is, can SKIM deliver the geophysical products with the required performance that fulfill the science objectives? And our target is to give you the evidence that SKIM products can indeed meet the mission requirements. And the tools we're using to do that are end-to-end performance simulators, electromagnetic models of the sea surface, realistic reference scenarios and test data, and a set of objective metrics to perform the assessment. We start with a call, E9 call. We have a proposal. From that proposal, we develop mission requirements and fundamental product specifications. And the first time that we use simulators is now to translate those product specs into the products that we need. We also assess the products using simulators, and here we have the SKIM end-to-end performance simulator supported by other tools. The outputs of those simulators, together with campaign data, inform our studies on science and societal benefits. And this allows us to confirm that indeed we tried to meet our level 1B and level 2 requirements and confirm the scientific readiness levels. I'll focus in this talk on these elements only. We want to quantitatively assess the specific performance targets against which our results can be scored. And we've derived a series of metrics, which are in the report for mission selection, directly against user needs and the mission objectives themselves. And you've seen before that we have JCOM requirements representing operational oceanography and GCOS requirements as a goal for SKIM representing the climate community. Our requirement is to provide a total surface current velocity to less than 15 centimeters per second, or 15% of that measure, whichever is highest, with a goal of 0.1 meters per second, 10 centimeters per second. Where are we today? These maps show you what you can obtain today from 3 months of Sentinel-1B C-band data, and these have been processed in the tropical areas to give you an estimate of the line of sight, just one line of sight in the radial direction here, of the total surface current velocity. You need 20 years of measurements in situ to do the same job. These are drifter velocities on the right, which have been processed to provide an analogous measure to the Sentinel-1. So we can have one component of the total surface current velocity at 200 kilometers every 3 months with a precision of about 30 centimeters per second. That's what we can do today. And SKIM aims to measure the total surface current velocity and Stokes drift every 10 days, less than 15 centimeters per second. So, uncertainty propagation. We have to do uncertainty propagation because we want to understand the relevance and the quality of our simulation. So all sources of error have been established for SKIM by industry and scientists working together as a team. At level 1B, errors have been linked to uncertainties, and the errors are accounted for in our analytical models. And our uncertainties are then propagated through our system. To remind you of SKIM products, starting on the left, we have our nadir altimeter processing scheme. A lot of the processing is performed on board in the FPGAs that Eric explained, and this leads to a traditional nadir altimeter product, not only for the ocean, but also for the land surfaces, the rivers and lakes. The level 1B products that are edged from SCAR off nadir beams include the Doppler UGD, the geophysical Doppler measurements on one side, and on the other side, the backscatter and Doppler modulations for the wave processing. These are processed into level 2 products, which are then fed into our estimates of line of sight total surface current velocity measurements. These are then gridded, as Fabrice explained, into swath-based products of a total current vector, which is not available today at all. We can further process these into a time analysis product to give level 2D products 10-day maps. I'll try to cover most of these things in this presentation in terms of performance. So SKIM uncertainty propagation starts by choosing the right reference scenes, and we use state-of-the-art models, which I'll touch on a little bit in the presentation. These are our representation of truth, and therefore we try to use the best available today. And from this we can form a level 2A product suite. Here we propagate uncertainties from the way we manage the input data sets, and from that we can propagate those uncertainties through to our level 2B line of sight velocities. There are many errors and uncertainties that we've tried to capture here, and I think in terms of the level 1B at the end of phase A, we've actually made good progress, and you can see two numbers in brackets here. One is the starting point, and the second number that you see is where we've ended at the end of phase A. So you can see we've made an improvement as we learn to understand the instrument, its characteristics, and also the way we've set up our simulations. These are then passed into the level 2C and level 2D processing, where we produce our flagship products for users. In terms of the simulator framework, we use a series of input sources. We have our reference models, realistic scenarios, test data sets, electromagnetic models, the SCAR instrument parameters, orbit and sensing geometry, and the uncertainty budget. These are used to create a scene, and we run those into our level 1 end-to-end performance simulator, which can run 10 to 20 turns, and 10 to 20 turns is a huge computational burden, where we go from level 0 raw data right the way through to a level 2C product. This is supported by a series of specialized and specific simulator tools so that we can optimize our end-to-end simulator, including electromagnetic interaction with the sea surface, including traditional tools, because we don't really need to reinvent all of the tools for altimetry. We have many of those tools available. So for our nadir beam, we can fall back and use existing standard tools that are used in Sentinels, Copernicus Sentinel-3 and Sentinel-6. We also support all of this by knowing that in order to assess performance of SKIM, we have to go global. We have to understand how our global environment over the ocean is performing, because SKIM is a mapping machine. SKIM is about mapping the global ocean surface currents. And here we have a level 2 parametric simulator. We call it Skimulator, and this has a global capability from level 2A right the way through to our level 2D products. The measurement uncertainty estimation comes from the end-to-end performance simulator, and this we will talk a little bit about later in this talk. We have our performance evaluation, which is then supported by dedicated performance metrics, which are written up in the report for mission selection. And that is the framework that we use today for SKIM. The end-to-end performance simulator, we have, as I mentioned before, level 0 right the way through to the level 2C products. We address all of the error sources, and we have established a heritage tool built on the knowledge that's been gained in the community, both in industry and in science over the last 10 years. We can also prototype algorithms using this simulator. One specific aspect of a simulator for a radar is to understand the test scene that you're using. And we use state-of-the-art surface ocean modeling with wind seas and swell wave spectra. We have a 2-scale composite grid right down to 80 centimeters. So it's a very, very fine grid, where we try to resolve the wave scales with minimized computational cost. And we have a resolved and a non-resolved component of the full spectrum that is included in that. And we've had specific attention that's been paid to the decorrelation and the Doppler shift from unresolved waves. What does that really mean? Well, we're going from roughness, and here you can see a visual image of the sea surface from the simulator. We had topography, we had local incidence angle variability, the normalized radar cross-section, the radial velocities, and the SKIM range gates, which have been very accurately simulated. Because what you want to be able to do here is to see the ocean surface in the way a radar does. You need to see it with radar eyes. Are you ready? This is what the radar sees. So if you're from 1969, 1970, this is great. But that's what the radar sees. So you can see it's very complex. We have a dynamic environment in which we're trying to run the simulations. For the level 2 parametric simulator, we take all the experience and knowledge we've gained in the SEEPS, the SKIM end-to-end performance simulator, and the measurement uncertainties are passed into a more traditional simulator that's modularized, going from level 2A right the way through to our end products, again, propagating all the uncertainty. A very important point is that many of these simulators are open source. Team SKIM believes very much that in order to involve the community, to foster the community, and work together with the community, the way to do that is to work with open source. It gets users into the data very, very early on. So how do we develop our global scenes? We use the MIT GCM, which is a state-of-the-art ocean circulation model, including the surface current, sea level, and sea ice. It has a horizontal resolution of 1.5 kilometers and a very shallow upper layer, which is very important for us. This is complemented by WaveWatch 3, operational and research model that's state-of-the-art, includes Stokes drift, and is at 1/4 of a degree. Those reference test scenes are then used to generate simulated level 2A data of Doppler line of sight and backscatter, simulated level 2B data of current line of sight and 1D wave spectra, and those are combined to give a single swath total surface current velocity that in this image here have been shown for several orbits, and a level 2D multi-day composite. We assess our performance at global level and in regional levels, so it's Gulf Stream, for the equatorial Atlantic, and in the FRAM to capture some of the high latitude issues that we face. Now, this is an animation from the MIT GCM. It shows you what is going in to our simulator, and this is the data that we use to assess performance. And I draw your attention to the little flashing dot. That is roughly, I can't guarantee, but roughly that is about 30 kilometers. And we've played around with fonts to make sure it is. But you're looking at something like that. And of course, the red dot in the bubble plot there is showing you where we're pitching ourselves with SKIM. And it's right in the middle of many, many processes, which are sort of captured in this animation. You can see the internal tides, you can see the currents, you can see the near inertial oscillations, which are not measured by altimetry, but will be measured by SKIM. In terms of reference scenarios, what we're trying to do is perturbate our understanding and our models with differences between the moving sea surface, the waves, and we perturb using wind vectors at different angles, and we perturb using different currents, again, at different angles relative to each other, because this is the real world. And so we are trying to make sure we've got realistic test scenes to assess the SKIM performance. The first thing we need to do is verify what industry tells us. It's not that we don't believe industry, but we want to be sure from an independent perspective that, in fact, the parameterization of instrument performance being passed by industry is indeed correct. And so the SEEP simulator has been driven very hard to produce an estimate of both concept A and concept B. And you can see the performance metrics there. We have a particular shape, which is due to the fact that we have a rotating beam around the azimuth. And so the Doppler changes as you fly forwards. You have a Doppler signal, and your azimuth is changing, and therefore you get differences. What we can see here is that SKIM can indeed meet the level 1 pulse pair performance requirements as stated in the mission requirements document. And we have an analytical model which is embedded in SEEPs, which further confirms. Fine pointing, Eric has mentioned before that I'll pick up from him. Now, fine pointing is indeed fundamental to a Doppler mission. And for this purpose, the technical team has included all of the AOCS sensors, and one concept shown here. The other concept has a slightly different arrangement, but indeed they're all bolted, hard bolted to the instrument frame. So we are measuring as close as possible to our antenna. And the principle of our fine pointing calibration is that we have an algorithm that takes changes in the gain patterns of the antenna as it rotates around the azimuth, and we're fitting harmonics to the antenna rotation frequency that are modulated as we move along the orbit. There are changes, and we know there are changes, and we expect those changes because we're using an off-axis geometry on the antenna. But as long as those harmonics are stable in time, they have a nice sinusoidal signature. Eric has already shown a little bit of that, but these then can be unambiguously separated from the broadband unstable signatures of the ocean. So the ocean is nice and is a great target to do this calibration. We don't expect the ocean to suddenly change direction in currents, and we don't expect the waves to suddenly die. We can rely on our ocean to do the job. Now, the algorithm we use is not new. It's been used by many satellites. And Jean-Marc Delouis, where are you? He's at the back there. If you want to speak to him in the icebreaker about what we do, he can fill you in all of the details. I shall take you through the basics. He developed the algorithm that's been used by SKIM, which is also used by the ESA Planck mission. Essentially what you see here in the plot is you see the yaw error, which is associated with largely thermoelastic deformations on the antenna as it rotates around the azimuth. And this is actually capturing one orbit of data. And we can see that thermoelastics is dominating the changes. Now, our conical scanning geometry means that we can look at the same part of the ocean from different azimuths at slightly different times. And we do not expect the ocean to change dramatically. Therefore, we have a unique signal that is almost orthogonal to what you see from the spacecraft. And so our algorithm exploits these two different things by making sure that we can separate the geophysical signal from the satellite pointing. Let's look at it in a different way. Same data here, but now what we're going to do is we're going to unpack it, and we're going to unpack it along the orbit here. And you can see if we were to do a 3D plot, there'll be slightly little ripples on the top of here. But you can see from this plot, they're not enormous ripples. This is then embedded into our simulator, and we have, this is the map we get here. We don't have polar regions, and we lose areas here because of the land. When we apply the algorithm at the bottom, you can see that we separate out orthogonally the geophysical signal from the signal that we expect from the spacecraft with very small residuals. We also have thermoelastic data during the phase A from an equinox orbit and a representative case of summer and also of the winter conditions. So we have enough data here to actually simulate the entire annual cycle. Looking at in a power spectral density view, here we have the scenario. It's based on missed pointing data from industry, as I've explained. The orange curve is the other uncertainties I mentioned before within the simulator, which are geophysical. And you can see in the red line on the right, this is the signal that we want to retrieve, which is dramatically different from the blue signal, which is input, and the residual is in green. The result is that we can demonstrate here our fine pointing data-driven calibration manages all missed pointing errors from level 2, level 2B, and that's our fundamental product to go further. If you want to have another view, this is the spatial view, and what we've done here is grid up 6 days of data. And this is the input to the fine pointing. There is a reduction in the error here. We've got 0 to 5 meters per second on the right. After we apply the algorithm, you're down to less than half a meter per second. And you can see the geophysical signals. And there's a slight residual. And notice that that residual has patterns. And those patterns are related to the different modes of error within the algorithm. And in time, those can be exploited. So in fact, as the mission duration increases, we get a better and better and better fit. Nadir altimetry performance. We have a nadir beam. The nadir beam will be used for altimetry and also for rivers and lakes on the land as part of the standard scenario we have for SKIM. The requirement in the metric is to have a sea surface height computed as less than 3.2 centimeters after all the geophysical corrections are made. You can see in the table there, the altimeter range is about 3, the same as JSON, JSON 3. After we apply the RMS orbit radial component uncertainty, we reach an equivalent performance. And at the same time, for those that are interested in the significant wave height, we do slightly better because we're at Ka band. If you look at this the power spectrum of here in red SKIM, and Sentinel-3 is in green, I think. I can't see the line here. And in blue, we have JSON-3. We sit between the two. And of course, the hump for the oceanographers in the room that you see at a wave of about 10. What you see there, that's because that's a low-resolution altimeter, whereas SKIM and Sentinel-3 are both SAR altimeters. But we can meet the level 2 nadir altimetry performance requirements. Effective resolution is a question we're always asked. So you say you can measure at a grid posting of 30 kilometers. So what do you represent? And so a study was performed together with Dudley Chelton. In fact, Dudley did most of the work to try and look at this. And what you can see in the image, we have an error-free scene, and we have what SKIM would retrieve using a noise of 15 centimeters per second, and the errors are at the far right. And you can see here for two different characteristic signal-to-noise values of 2 and 3.16, our effective resolution, which is here, lies at around about 30 kilometers, commensurate with our grid spacing. And of course, this is something that we're doing on paper, and as the mission develops, we will look more and more at this as we understand how the instrument would evolve should it be selected in the future. For the wave performance, waves are important for SKIM because this is how we actually retrieve our wave Doppler, which is the largest source of uncertainty on the retrieval of the currents. And so we need to be able to separate the wave Doppler component from the rest of the ocean wave field. And you can see the little animation there to remind you earlier. So the conical scan design of SKIM, again, is exploited, and the Ka frequency is also exploited to make sure that we can get a very high fidelity wave spectrum. We have a simulation here. We start with the WaveWatch 3 model, state-of-the-art model with these characteristics, and you can see the wind direction, and you can see the swell peak there and the wind sea in blue. This is what our simulator, the R3S simulator, would retrieve for the SWIM KU-band case. And SWIM is ambiguous in terms of the wave spectrum. You're not sure in exactly which direction the waves are coming from. There's 180-degree asymmetry. Now with SKIM, what you can do is, because we have Doppler at the same time, then we can resolve that ambiguity. And because SKIM is a low noise instrument, and we have a better fidelity at K-band, you can see here the noise is reduced. And if you compare that to exactly the same conditions that we're trying to simulate from CFO-SAT SWIM, you can see the benefits of SKIM here. So here we really are expecting very good wave mission performance. We can go further though. If you look at the range resolved wave spectral intensity, we have a scenario here where we look at the wave spectra, and what you're seeing here is how you can see the swell and the wind-sea peaks in those spectra. These are the 1D spectra, but you can also see they're not sitting at zero. They're slightly biased. This is the results of 100 simulations, and we can debias based on the data, and you can see here that we clearly separate out the swell and the wind-sea, and at the same time we have signal below our requirement of 30 meters wavelength. That's important because it's that wind-sea that is used then, that part of the spectrum, that is then used to compute the spectral moments from the spectrum that are used to drive our wave Doppler correction. So we meet all of those requirements, and we believe that we can do better than our requirements. So level 2C, this is the current. This is the current that most users will want to actually access and want to use in their daily work. Here we're looking to start with at regional level 2C total surface current velocity performance. And our scenario is 1 month of SKIM data from the simulator at a 1/4 of a degree resolution with the full propagation of the uncertainties. On the left you can see truth, and on the right you can see the retrieval. Is that good enough? Not for most people. They want to see numbers. So the numbers that you have here for the cross-track performance and the along-track performance, there are 2 numbers in the green column that you can see to the left. For the Gulf Stream, the Equator, and the Fram, the top number is the total surface current velocity. The number in brackets is the Stokes drift. Stokes drift is, of course, much smaller. But in all cases, we meet requirements, and in some cases, we approach and even meet our goal requirements. So at the moment, SKIM can meet regional level 2C performance requirements based on our simulations at the end of phase A. Signal to noise is important. It's fine to show regional products in this way, but in fact what you want to see is what is the signal to noise across the globe. And this is the signal that we will get for a scenario of 1 year of SKIM level 2C at a 1/4 of a degree with the full propagation of uncertainty and flagging of errors, rain for sigma 0 blooms removed. And remember, we don't include all the data around the coastline for this particular scenario. This is the noise figure that we get from the simulators, and here is what you expect. This is what we expect from SKIM in terms of our signal to noise. And remember, before I showed you the simulations of Dudley-Cheltham, where we were looking at signal to noise between 2 and 3, here we take a worst case scenario. Where we see green, it's good. Where we see deep green, it's very good. And where we see pink, that's where we may not expect. At the moment, using the current algorithms that we have a little bit of work to do. But indeed, we find that we cover most of the global ocean. And indeed, the performance is here. Again, in the top number gives you the total surface current velocity, and the lower number at the bottom here gives you the Stokes drift. So at the level 2C, we're meeting our requirements and approaching the goal in both cases. The level 2B data are used to actually drive performances at level 2D. And here what we're trying to do is to see if we can address the GCOS requirements, which are for 5 centimeters per second over the global ocean. And we've decomposed our signal into a cross-track and a long-track, eastward and northward components. And our scenario is 1 month, in this case, of level 2D data from the level 2C data from the simulator on a 0.1 degree grid resolution with an uncertainty over 10 days. Our metric is to look at the differences between the simulated level 2D compared to the input truth, and to see if we can meet that requirement. And we're marginal. For the northward component, we meet the requirement very easily, and for the eastward component, we're nearly there. But I must point out that in this particular scenario, we've taken a very brute-forced, very honest approach. We're not using optimal estimation. There's no underpinning model in the combination of data here at all. We've taken no account of tides, and there are far, far better ways to do this. We choose not to do it at this point. We don't want to be accused of cheating. However, users will, of course, either assimilate the data into a model that can do advection for you, or they will take an approach where they derive background error covariance and some correlations to do the job properly. So we're very, very pleased with the report, with the simulations that we have here, and in fact quite excited when you see the animation. So the details of these kind of products, what you can see here is an animation of how we would use the level 2D data, and you're looking at divergence in the equatorial Pacific Ocean. And for reference, on the right-hand side, you can see here what we get from observations from a cruise. It's Perez and Kessler in 2009. And you can see most of the structure, the dynamics is in the very, very top of the ocean. And that's exactly what SKIM is catching. And this is a map every single day of divergences. And this is the kind of information that's required to understand what's going on in the tropical ocean and how it relates to the applications, in particular for ocean mixing, for the air-sea fluxes, linked to our weather forecasting, because what happens on the distant ocean affects you at home on the land, together with the biogeochemistry and the biological productivity. So, we also ran a campaign, the Drift for SKIM campaign, and during this campaign we flew aircraft and we ran ships in an area off Brest, northern Brittany. Brest has an HF radar system, and so we made sure we flew our campaign within that area. We flew a star pattern, so that we can look at different azimuth relative to the current and the wind direction. Now, we can't mimic what SKIM does in space, and we didn't even attempt to mimic what SKIM does in space. The satellite flies at 7 kilometers per second, and we can't do that. And we have a radar, though, on the aircraft that we can use to try to mimic elements of what SKIM will measure. And in particular, what we're interested in is to beat down and verify the uncertainties on our wave Doppler algorithm. And so we wanted to validate using a series of drifting buoys, which you can see on the left here, ready for deployment, and aircraft data. What you see here is the results of the campaign, and you're looking at the azimuth variability of the wave Doppler and the velocity measurement in meters per second. You can see in the blue curve the occurrence that were taking place at that time for 2 days. There's a top panel on the 22nd of November and the bottom panel on the 24th of November. We're both in KA here using the Coraddoc instrument. It was developed in part by Knez and Ifremer together. In the blue line, you can see what we are able to simulate for the geophysical Doppler. And in the green line, you can see what we, in the blue line, you can see what we simulate for our wave Doppler. In the green line, you can see the simulated geophysical Doppler. And the measurements there in red dots show that we have a good verification of our approach. If you translate that into a restituted current, in blue you can see the magnitude of this wave Doppler and why it's so important that we get this right. It's the dominant signal that we have to remove from the geophysical Doppler signal. In the circles, you can see independent measurements, one from an SVP drifter, which is drogued at 12 meters, representing what you would have in the operational validation infrastructure we'll use for SKIM. You can see in light grey a Cathay drifter, and this is a drifter that has a drogue sitting at 1 meter in the ocean surface, so that's representing the total surface current velocity, and a completely independent technique from the HF radar system in Brest. And you can see that all of those uncertainties add up quite nicely together to verify our wave Doppler algorithm and the ability of SKIM-like data to retrieve the ocean surface current using infrastructure that oceanographers understand and can use. This is published now in a paper. I think the paper is now either online or it's about to be online, where you can review the entire SKIM Drift for SKIM campaign. So we can say that our SKIM version 1 wave Doppler algorithm has been validated, and we're very pleased about that. Scientific maturity. During the process of the SKIM work, we ran an inventory assessment at the beginning of phase A, and we ran a second assessment, a scientific readiness assessment at the end of phase A, and we tried to actually capture where we started from and where we finished. And you can see here, and as reported in detail in the report for mission selection, we've attained an SRL of 5. That's not enough. In terms of maturity, we need to establish a scientific roadmap to see where we want to go next. What is it that needs to be done to make SKIM better? What does it need to be done to make SKIM great? How do we assess and how do we reach an SRL of 6+? We know that we need to improve our wave Doppler. And so we know that we will need a campaign in particular to look around the ice edge, using a priori swell spectrums could be one way. We need information propagated from previous orbit measurements. We haven't looked at that yet. We didn't have enough time. We also want to improve the understanding of the retrieval of the Doppler within the coast and close to the sea ice edge. We know we will get good results, certainly in line of sight. Where we have to understand is what is the azimuth diversity for a given coastline and for a given SKIM swath, so that we can understand how far can we go and how do we actually open out the uncertainties for the wave Doppler correction. We want to test the use of multivariate machine learning techniques to optimize the wave Doppler algorithms using the data itself. This is an efficient way to proceed. And we want to prepare the ocean modeling community for application of SKIM data. In other words, help them to develop the observation operators that are required in order to fully exploit SKIM data. It takes time to do that, it takes effort, and it takes money. And we want to be sure that we bring our community with us. We will be developing tools and an approach to explore beyond geostrophy. Today we're so used to geostrophy, and when we introduce new concepts, such as we're here with SKIM, in terms of measurements, where we will have for the first time global repeat coverage, total surface current velocity, and the Stokes vector, it will take time to learn how to use those. However, we know from the work of in ESA interaction, we know from the results and the presentations earlier that these are essential for us to understand how the ocean interacts with the atmosphere and how we can actually progress towards understanding better societal benefits. We'll refine further the data-driven calibration fine-pointing algorithm to exploit the patterns that we see in the residual uncertainties, as I mentioned before. And of course, we will develop synergy with all the other satellites that we have in space today. We didn't touch on any of that. Scatterometry, sea surface temperature, ocean color, salinity. All of these, together with an ocean current, really are going to give a very powerful data set for which to drive science and society. We didn't mention the delta K technique. SKIM itself employs a variant of the delta K technique. We have on board a classical situation where we are able to evolve our algorithms. It's rather an unclassical situation. And so we want to do more work with the delta K technique as we move forward. So in summary, SKIM, it's the first global coverage Doppler mission. It's our HF radar in space, we say. It'll provide measurements of the total surface current velocity in waves with regular, repeat coverage and dense sampling in a way that we've never had before. It'll address the science and societal scientific needs and the living planet challenges. And through the performance results that I've shown you here, we can deliver the geophysical products with the required performance that fulfills the science objectives. And we've assessed the critical scientific areas of maturity and risk during this whole process. So SKIM is a high-performance science mission with long-term implications for the future of science and science applications and Doppler oceanography. So thank you very much.
So it's me again. I will conclude the SKIM presentation with an overview of the programmatic assessment. But before starting, let me take a few seconds to clarify one point. You will hear in the context of the programmatic assessment for some domains a very similar statement to what we have heard this morning. This is not related to my confusion or to a wrong copy-paste of slides. Is thanks to the excellent work that has been performed by all the teams and individual involved in the preparation of the mission, and it's thanks to their expertise and dedication that similar statements can be made. So, having said this, let me start also with, for SKIM, with the critical areas and technology maturity status. So SKIM is considered a technically feasible mission, but challenging within the programmatic constraints applicable to the E9. For the satellite platform, the concept, as explained by Eric in the technical presentation, are based on either reuse of existing and flight-proven solution, as for concept A, where heritage from the Copernicus Sentinel 5P and the Seosat Ingenio platform has been considered, or from standard products to be developed, as is the case for concept B, where the reuse of the Nucleus standard platform to be developed for the Copernicus high priority candidate missions has been considered. Also, for this case, some of the platform units will require some mission-specific adaptation or will benefit from parallel development to achieve high TRL. In any case, the mission-specific custom design for the platform units are all based for both concepts on mature technology that have already a TRL higher than 5 and do not require, therefore, the implementation of early pre-developments. As explained in details during the technical presentation, the SCAR instrument derives significant heritage from the SWIM instrument for what concerns the overall instrument architecture and the antenna design, and for the Poseidon 4 altimeter and the K-band radar interferometer of SWOT for the instrument electronic, digital, and RF stage. Nevertheless, the needs of SCAR require some specific customization, and critical elements have been identified clearly in the technical presentation. The mitigation of the associated risk is being performed by relevant technology pre-development that are ongoing and will be continued during phase B1 in order to achieve the required TRL of 5 to 6 by the end of this phase. So this table is again showing an overview of the technology pre-developments, showing the TRL at the start of phase A, the objective achieved at the end of phase A, and according to the roadmap and plan pre-developments, the achievement of TRL at least equal to 5 at the end of phase B1. I will now describe shortly all the relevant activities, starting with the onboard processing architecture that was described in detail during the technical presentation. As already mentioned, a baseline FPGA solution and architecture have been identified, which consists in 2 FPGA for the onboard processing plus 1 for the data formatting, as shown in this architectural sketch of the OBP. The complexity and the margin for this solution have been assessed, and the MATLAB reference code has been completed with analysis of the resulting OBP data currently ongoing. As shown in this sketch at the top right, these are the activities completed and the ongoing analysis. The next step is the start of the quantized OBP coding that will lead in the end to an implementation and test on a representative breadboard to be carried out during phase B1 to reach TRL 5. For what concerns the grid modulator, the first option, or better baseline being assessed, consists in the manufacturing of a relevant breadboard, which has been completed. The testing under thermal vacuum is planned in August 19, and the final review in September 19, which will lead, if as expected, a successful outcome to the achievement of TRL 5. For the second option, dealing with the high voltage transformer and grid modulator, for this parallel option, the breadboard design is in progress. The manufacturing and testing will be performed during phase B1, and if successful, will allow to reach TRL5. For the one-way antenna rotary joint, the final design is underway. The manufacturing readiness review is planned in September this year, and the testing should be completed by the end of this year to reach TRL5. For the high power isolator and circulator, the preliminary design has been completed. This more up-to-date sketch of the identified solution were performed during the technical presentation. The RF performances have been simulated, and the testing, excluding the multi-action aspects, will be completed by November 19, reaching TRL5, with the execution of the multi-action testing planned in Q1 2020. TRL6 will be achieved. For what concerns the low noise amplifier, and in particular the improvement of the noise figure and the assessment of the safe operation areas, two different candidate circuits have been selected to improve the noise figure of the LNA. The RF characterization has been completed, and the achievable performance improvement have been confirmed. The two selected dies have been subject to input power step stress test, which have been also completed. You see the selected dies under test in the picture. For both devices, the dies which have passed all steps of the stress test have undergone, we can say at this point, the live test. At the time of writing, the live test was not completed. We understood that this has been completed during these days without anomalies, and therefore also for this aspect we can state the TRL5 at the end of phase A. For the ferrite assemblies switch drivers, the breadboard testing has been completed, achieving TRL5. You might have seen the switch driver breadboard on display during the coffee break. Again, this is showing the board under test, and a zoom of the board, as I mentioned, was available during the coffee break for display. These tests have confirmed the operation at the SCAR PRF of 32 kilohertz. The power consumption assumption have also been confirmed, and the switching time has been validated. Now, for what concerns the development approach, SKIM will follow a traditional phase development approach with phase approach with reviews concluding the different phases. The platform and instrument pre-development development is decoupled as much as possible. For the platform development, both concepts are based on an engineering model, proto-flight model approach. The electrical and functional verification at satellite level is performed on a satellite EM, which consists of simulated recurrent units plus EM of modified units, plus an EM of the SCAR central electronic or relevant backbone. A structural model is planned at satellite level for the mechanical qualification. For the SCAR, an EM PFM approach is baseline for most units, except the ferrite assemblies and the duplexer and HPA, which will undergo an engineering qualification model, flight model approach, and the antenna rotary mechanism assembly, for which a qualification model has been included for lifetime testing. So the SCAR proto-flight model will be mounted and tested at satellite level for functional and performance verification. For what concerns the schedule, this is driven by the instrument development after the preliminary design review, that is for the phases C and D. A launch by end 2025 is not considered feasible with adequate margins. A launch by mid-2026 is feasible but challenging and requires an optimization of the development approach and the schedule, taking into account the associated risk. This simplified Gantt chart is showing again the schedule considered feasible with a launch by mid-2026, assuming a start of the development activities in the second quarter of 2021 with a relatively short phase B2 and a combined phase CD for a duration of slightly more than 4 years. To conclude, considering the outcome of all the preparatory activities that have been carried out within a compressed and very tight schedule, it is judged that the critical scientific areas of maturity and risk have been assessed and there are no major issues of concern to the scientific development of the SKIM mission. The required SRL5 is considered reached at the end of phase A. Assuming an expected successful outcome of the ongoing and planned technology pre-developments, the maturity of the critical technology will reach the required level of TRL higher than 5 by the end of phase B1. The development schedule is compatible with a launch in the 2026 time frame. And therefore, the SKIM mission concept is considered sufficiently mature for implementation as the 9th Earth Explorer. This concludes my presentation. Thank you for your attention.
Again, as you have experience with before, we have to move some chairs, and I would ask the SKIM scientists on stage. You wait for chairs. Yeah. No, but the chairs are just coming. Again, we have 2 microphones available. Thank you very much, and a catch box. So maybe we should have it in action, and maybe some of you guys over there ask some questions so that we can see how this is really flying. Yeah. Okay. So Craig, you're chairing? Yes.
I would like to ask if we can have the team slide up on the back projection.
You needed to put it here.
We want the logos, yeah?
No.
Okay. Team slide.
Yeah, just here. And the scientist.
Everybody ready? So I'd like to invite questions from the floor to the SKIM team. I have one in the center. Oh, a bit of fun.
Simon Tett, University of Edinburgh. So I was really excited at the beginning of the presentation when you talked about other things that would come out of SKIM, in particular ocean carbon cycle and mixing. But I don't see from the presentation how those products or information would be developed. Would you be able to amplify on that?
Sorry, I didn't understand the question.
So my question was, at the beginning of the presentation, there was the idea put forward that from SKIM, we would get information on upper ocean mixing and the ocean carbon cycle, which are really important issues. But from the presentation, I don't see how that follows. So I'm asking the team to amplify on that point.
Okay, thank you. So, Jamie Shuttler, can you take that, please?
Yes, so I'm Jamie Shuttler from the University of Exeter. So the exciting thing about SKIM is it will enable us to start isolating the different and extracting the different components that are actually controlling this exchange at the surface. So we'll first of all be able to focus on the waves, and then also the currents and the interactions between them. And then in combination with the fact you METOP, it means you can then also start looking at the wind. So you can start kind of teasing out all of the different processes which are controlling and altering this exchange. And it's the fact that the measurements are all coincident, and this has not been possible before.
Thank you. Question at the very back.
The upper ocean temperature and ocean mixing has been recently shown to be highly dependent on the horizontal gradient of the current, so the surface gradient of the current. What kind of gradient can you resolve? This is related to the last question.
Fabrice, could you take that?
Oh, sorry, Mark Barassa from Florida State University.
Yes, sorry, please announce yourselves. Yeah, you ask a question.
So yeah, Fabrice Ardouin from LOPS. So basically, we have these different level products, but the flagship product is really the level 2C data, which is on a grid at 30 kilometer resolution with a posting at 5. So that gives you an idea of the gradient of that level 2C. Of course, there's also the level 2B with more, higher uncertainty, but that's available at high resolution. So we have these different products at different resolutions.
Thank you. There's a question down here first, and then David Wolf, I think, is probably next.
Yes, Anasini Viradne from ETH in Zurich. I have two questions. So the first one is again on carbon cycle. So by how much do you expect that you could reduce uncertainty in the carbon sinks from the SKIM measurements? And the second one would be regarding the radar measurements. I was wondering, I mean, I'm not a specialist on radar measurements on the ocean, but I was wondering, how much do you get really from satellite measurements? I mean, it's a 5-year mission. How much would you be able to get, for instance, from airborne measurements if you were to do snapshots? So, I mean, what is the advantage of having a satellite mission versus just some airborne measurements?
Okay, thank you. There are two questions there, so can I ask you to refrain from asking two questions? Please ask one to give other people a chance. The first question is to Jamie, and I think the second question would go to Adrian.
Okay, sorry, could you, I didn't quite follow the question. Could you just repeat the
Your
first
first question, please.
Thank you.
The first one was the carbon cycle. I mean, that was, again, a similar question as somebody asked before. I mean, I still wonder about how much you really expect that this could reduce uncertainties in the carbon sinks.
Yes, okay, thank you. So with wind is the major proxy which is now used for describing the exchange. And we know that we capture about 80% of the variability we have in situ data with just wind. However, that only works in some of the cases. So we know there are lots of places where that doesn't work, and we know in particular that it works very poorly, or at least the processes are very poorly understood in the Arctic regions. So as the Arctic becomes ice-free, we have no handle on how well these proxies are actually going to behave. And so there's lots of situations like wave current interactions in strong fronts in the Southern Ocean when we're getting internal circulation and moving and upwelling, and these are all cases where the wind parameterizations start to break down.
So do you want to take the second question, Adrian?
Adrian.
Yep.
Adrian Martin for the National Oceanographic Center. So with an aircraft, is impossible to have a global monitoring of the entire globe in 3 days. So, yeah.
Thank you. Next question, please. David Wolf had one here, I believe.
Good afternoon. I think I'm actually picking up from the first two questions. I mean, I can see how useful if you like, the standard products for TSCV and the derivatives and also the waves, how interesting that is. But for me as a research scientist, what really interests me, terrifies me, is understanding the full interaction of wind, wave, and currents. And I see SKIM, and I also see two instruments on the METOP, which will be accompanying it, and various other sources. So I'm hoping somebody might give me a little bit more insight into what hope there is in teasing out all of the detail of wind stress, wave characteristics and currents from that whole package.
Peter? Okay. Please can we have some questions to some of our other MAG members? Okay. Last one for you, Jamie. You're not answering anymore.
So an example of this kind of thing is, as you pointed out, we can begin to, the total surface current velocity is the velocity that's relative to the wind. So immediately we can start to investigate what are the differences are when you just take that into account and it's actually opposing the wind. How does that change the turbulence? We can also start to pull out the different wave parameters from the wave spectrum information we've got. So, for example, you can look at the total amount of kinetic energy that's actually being pushed onto the surface of the water as a result of wave breaking. So in that way, we can actually isolate the component that's responsible due to breaking waves in terms of gas exchange. So in this way, we can slowly start to pick it apart and actually, at the very least, identify which ones are the dominant effects under which scenarios and which places.
Thank you, Jamie. There was a question on this side here.
Thank you. Tony McNally, Principal Scientist at ECMWF, again, sorry. So one of the things we are measured by now is our success in the forecasting of tropical cyclones. And tropical cyclones are quite a challenging environment for any instrument. The passive microwave and infrared pretty much give up for air-sea interactions, which is the key thing to get that air-sea interaction. Could anyone in the panel say whether it's likely that SKIM will operate successfully in a tropical cyclone environment with heavy rain and breaking waves? And will it make our forecasts better or worse?
So, Alessandro, could you take that one, please?
I can reply on the heavy rain. Heavy rain, there is no way we will, we have to be frank, so will not work properly because heavy rain will attenuate. We know KA has several advantages, but also has some disadvantages, and a clear drawback is attenuation in rain. And actually, you can experience that if you have a satellite TV dish, because sometimes they have a Ka band receiver, and if there is a big storm, the signal will be attenuated. On top of that, there is another issue. So the attenuation means, of course, that your signal-to-noise ratio will decrease, and of course, the performance will go will worsen terribly. The other problem is that, especially if the rain is patchy, I mean, if you are doing Doppler from space, your worst nightmare is to have non-uniform beam filling in your footprint, okay? And of course, this, I mean, will be a typical scenario where this will happen. But we will, of course, be able to flag all this situation. We have two weapons. So the first one is that, of course, we are flying in constellation with the MWI, so the microwave imager. So that will provide a very good idea where the rain is. The second one, actually, if you look at the range-resolved Doppler from the instrument, also that will give us a lot of clue of what to flag out.
Thank you. Question, I think there was another one right at the very back. Oh, I was here, sorry. First.
Okay, Nico Sneeuw, University of Stuttgart, and also ACO member. In the report for mission selection, I read that there will be a land measurement phase of just a couple of cycles, I guess, for testing how the instrument works over land. But I was wondering whether that can be extended maybe for the whole mission. I mean, you would have a whole user community of hydrologists that you could make happy if the instruments are simply turned on over the continents as well. Not only the nadir altimeter, but also maybe to measure river flow.
I'll give this one to Fabrice Antoine, please.
So yeah, as you have noted, there's a continuous measurement over rivers and lakes throughout the mission. So we're talking here about the nadir beam, of course. And that would be actually fantastic measurements, because in that case, we can switch off the other beams and have continuous measurement all along that nadir in K-band at the very IPRF. That would be the best ever measurements of rivers and lakes. Now, for the other beams, there's potential for exploring many things. You can, think we can measure velocities of rivers, and actually that's a very key missing things in hydrology. People measure level, but the missing part is the river. So probably it will be easy for wide rivers, and there's a lot of things that have to be explored in general.
Can I ask Eric David to comment a little bit on the technical component of that?
Well,
what we have to do in the system to enable that is to make sure that we can operate the nadir beam as a regular altimeter. So we need to be able to operate it in open loop tracking mode, which we can. What we can also do is we are referencing the tracking for the experimental part that Fabrice mentioned. If you want to do something with the off-nadir beams, we can as well, because we are working out the tracking from the off-nadir beams from a nadir, but we can do that to a virtual DEM, if you like, a point that we just virtually track rather than with a real nadir beam. So that we can really position the off-nadir windows correctly also when we are flying over an inland sea, for instance.
Question here? Yes?
Jacek Piskowy, Institute of Oceanology, Polish Academy of Science, again, sorry. There were most questions were in my field, so I want to go further and challenge this SKIM team in new science. I was lucky to be at Scripps when Walter Monk mentioned today, noticed in satellite photography things that no one noticed, spiral eddies, which most probably wouldn't be discovered before the altimetry like SWOT or SKIM. So what do you think? Is there enough uncertainty in our knowing level of surface currents to be a possibility of discovering a completely new phenomena?
Well, my name is Devesh Stammer, and I'm speaking here as a member of the Mission Advisory Group and not as chair of the Joint Scientific Steering Committee of the World Climate Research Program. I just want to point that out. There are several aspects really in the flow field, in the dynamics that we don't understand. And Walter Monk, in fact, is a very good example that you mentioned. He had observations where he suddenly saw something. And so in many aspects, once we have the observations, you suddenly see, in fact, stuff you have never thought about. And for me, in fact, a very exciting example is also the mapping of bottom topography from altimetry, which was really not a goal of altimetry in the beginning, but we do it now to get a much better product than anything. For the velocity field, there are aspects that we know they exist, like the Stokes drift. We also know they need to be parameterized or included in climate models to actually produce better results, including carbon uptake or the exchange of heat and other things, but we have never observed it in a proper way. So I think there's a whole lot of theoretical understanding necessary for filling in this into the near surface dynamics. I mean, so far we have thought about a slab upper ocean dynamics, just sort of moving around with a 10-meter thick layer, but that's not the truth. In fact, we have seen today how complicated the entire structure is, and I expect really once you have these observations, maybe filled in with in situ observations, that you fill in a completely new corner in the dynamical oceanography.
Thank you. There's a question here.
Frederick Diaz, University College Dublin. Can you please clarify if SKIM will provide useful data to better quantify coastal hazards like flooding?
Fabrice, can you take this one, please?
Yes, in fact, as was shown by Craig, today we have only developed algorithm to develop TSCV measurement starting 30 kilometers from the coast. But we have a very good measurement near the coast. The wave Doppler just needs to be tackled in a different matter when the wave is much more variable, and this is what we will do in the next phase and what is planned. But today we have good confidence with what we see from SWIM data that was launched 1 year ago, that we will get some very good measurement near the coast also for the waves and the wave setup and for the flooding. So,
thank you. There's a question here.
Good afternoon. I'm Bruno Carli from the National Research Council in Italy. I'm not as an expert in oceanography, so my question will reflect my ignorance. I have more than one question, but we'll ask only one. Yes. In one of the early slides, it was showing the results of some in situ measurements of surface current. And if I read properly the slide, a large diurnal variability was observed. Now, a SKIM will fly on a sun-synchronous satellite, and I'm asking whether sun-synchronous measurements are able to capture all the information that is needed to track the transport of the surface current.
Thank you. Peter Brand, can you take this, please?
Yeah, that's an interesting question. There are a few processes varying on the seasonal cycle on Earth, particularly, for example, the tides, the sun cycle of the tides. And of course, we have an analyzing of these processes into our surface velocity data. On the other hand, for example, particularly when we think on tides, we have also the possibility, in contrast to pure altimeter data, that we have a wide swath. And for example, the internal tides are particularly a case where we can have much better information on the propagation of internal tides, which have a typical wavelength of 100 kilometer or something like this, that can be addressed and can be better understood and probably compared to observations. There are some other aspects with the diurnal cycle that has to be understood and also be tried to take into account, particularly when we have a diurnal cycle in the tropical oceans of the surface shear. And so the maximum shears in the afternoon after the solar radiation during the day strengthens. And we measure during approximately with this sun-synchronous cycle during 9 in the morning and 9 in the evening. And so we avoid this maximum shear of this cycle.
Thank you. There's a question here.
Yeah, I'd like Andy Watson from University of Exeter and an AGO member. I'd like to ask what your thoughts are on the use of SKIM measurements for oil pollution and similar events. You used those as in your advertising, as it were. And but it seems to me that there is a limited use here because you have a 29-day repeat cycle, and if such an accident occurs, one needs to know, relatively quickly. So, do you have a plan for? Are you going to try to map the Stokes velocity everywhere, for example, or try and parameterize it? How do you see it being used in practical terms? Would it be of any real practical use?
Eric van Spiel.
Yeah, thank you. Well, actually, a slight clarification. We don't have a 29-day repeat cycle. We actually, because of our wide swath and then sampling, we cover the entire ocean every 3 days. So that's already much faster, and that's already, it is indeed not up to date, but the velocities that we get, the TCSVs from SKIM can then at least feed into forecasting models. And at least the forecasting models are then as up-to-date as they can be. So I think that we can do quite a lot there, much better than what we have now.
That's one question here. 3. Oh, sorry. It's difficult to see, actually. I'm relying on Michael.
Hello, Athena Kostainis, Paris Observatory, AGO member. You mentioned a couple of times in your presentation the atmosphere-ocean exchanges. And I'm an atmosphericist, but for planetary bodies. But I was very interested in this, in particular about the near-surface region where you can form things like aerosols, bubbles, the exchanges with the gases. And I didn't find enough in your presentation to explain exactly what you expect to do with SKIM on that aspect. Can you tell me a bit more?
Fabrice, you want to say this one?
All right, so there's been quite a few work in recent years on the expression of aerosol formation and the effect of waves. So the new pickup of aerosols have been expressed as a function of wave height, for example, and that's because people had no other information. So if you take altimetry today, you have wave height, sometimes mean-square slope. By having the full spectrum, you can probably actually go beyond that and refine these aerosol sources. That's something that, yeah, we haven't explored directly. There was many other applications to look at, but that's one of the things that can be looked at in terms of future air-sea interactions and aerosol production.
There's a question at the back.
John Remedios, Director of National Centre for Earth Observation in the UK. So I'd like to thank both teams for their excellent presentations today. A comment, if I may, probably for anyone. Oh, no comment. All right, no
ask a
comment.
question,
Okay.
but not a comment.
Okay,
Please.
thanks, Craig.
Thank you.
I'll do that separately. Topic for tomorrow, probably. Okay, let me ask the question then. To me,
Thank you.
I'll put it this way. To me, it's just I had my hand up for half an hour, Craig. So I'm going to ask the question. So to me, this is really a physical oceanography mission. So because it's measuring a physical parameter. So what I'm slightly surprised and would like to see some examples of is what is it that this mission will do and what are the requirements on assimilation into models or on improving model representation of oceanography? That must be the critical thing this mission will achieve.
Thank you. Detlef, can you take that, please? Sorry.
Well, as we heard already this morning from Roger, that a huge step, and you will understand this and know this, is actually improving the models. Before you think about assimilation or initialization, it's really improving the models. And as I alluded to before, there are processes that we don't have in our models, and the Stokes drift is one of these, and all the processes related to these. And that's where it also becomes very interdisciplinary, because the whole geophysical cycle depends on these processes, including the vertical motion. And so actually, first of all, understanding these processes, which we don't yet in a proper way, we don't even have the parameterizations. And so improving the models, we do know, for instance, from runs from NCAR and others, without including the Stokes drift, you don't get the vertical movement, right, that you can get the carbon into the deeper ocean. So there's a whole lot of consequences once you fill this in. We have nothing like this in our climate models. So first of all, really get the theoretical understanding of this parameterization that you can build it in. The assimilation and all these things are a separate step. A next step, you can only do this once you have the physics in. You cannot assimilate data into crampy model. You first of all have to improve the model, otherwise it doesn't make sense. And that includes a vertical resolution and a lot of other things, and also means that you have to separate sort of chaotic processes from not so chaotic processes that you want to fill in. That's the next step for me. The first one is really improving the models, the understanding, the parameterizations, and that doesn't matter if it's a coupled model or just an ocean ice coupled model or so, to get these processes right. And I think this is a huge step forward.
Thank you. There's a question here.
Catherine Lambert, Fairfax, and member of SU. You mentioned you used or you will use or developed artificial intelligence method or deep learning method. So could you give us some precision?
Okay, you will take that. Fabrice?
Yes, in fact, there are two areas where we intend to use machine learning and artificial intelligence in the algorithm. So one is for the fine pointing, where we learn from the in-orbit azimuthal variability of the pointing, and this is really something that you can never do before waiting to be in space and really learn from the data. We had this experience from other missions, VSAT and Sentinel-1. And the other one is for the wave Doppler. Today we have the performance we achieve that are SRL5 with the current wave Doppler algorithm. It's a baseline algorithm. And when we get data in space, we'll refine a lot this wave Doppler algorithm by machine learning on the very wide diversity of cases that we will obtain, because so far we have been using simulations with a limited number of ocean conditions. So these are the two areas where we will really improve the quality of the products by machine learning.
Thank you. There's a question here, and then the final question to Jackie McGlade.
Thank you. I'm Joe Slinkowitz. I'm with NOAA Ocean Prediction Center, and my question is, in respect to safety of life at sea, what are your expectations of the capabilities in areas of strong ocean current gradients?
Okay. Who wants to take this one? You want to see it? Fabrice?
Well, we know that waves are affected by currents, and that's been studied, the Agurus current in Gulf Stream, for example, in a place like that. Today we have a very limited capability of resolving the gradients of the wave heights in the currents because of the poor knowledge of the current. And we've done some studies, as reported in some of the technical reports that come with the SKIM report, that typically you actually need a spatial resolution of around 30, 40 kilometer in a current field, otherwise you actually lose a lot of the gradient in the wave height. So that's just for getting the right wave height. Sometimes you get an amplification by factor 2 or 3 when the waves go through the Gulf Stream wall, for example. And given the time scales and the readiness, I think there's an ample way to use that data for forecasting and safety of flights at sea for this. That's one thing. The other thing is dangerous waves, especially dangerous waves from the side when you're crossing seas. And this is an area also with currents and wave refraction that we actually get a lot from this.
Thank you. Jackie.
Thank you. You use in some of your selling features this issue of using SKIM for tracking marine plastics and marine litter, obviously. And what we know, of course, is that apart from the garbage patch, most of it goes subsurface really quickly. So what's the kind of technology or technique that you would use to tell us about the point at which we lose it in the surface and it essentially goes down? Do you already have an idea about a kind of a service that might come out of that? And the final point is, are there no ladies interested in this project?
Well, if I may, before, just to answer your last question, I know I'm not supposed to, we did have a highly successful lady. We have two. Tanya Casal ran all of our campaign, and Maria Helen Rio was also part of our MAG, but unfortunately she was very good, and she's now an ESA staff member.
Yeah, so about the plastic, and indeed all the plastic that sinks down. So 2 short points on that. So first of all, I think it is still important to know the transport of plastic at the surface, because first of all, that is where most impact with marine life is, because that's where most seabirds, for instance, ingest the plastic. But the other thing is that the fragmentation of plastic, we think, happens a lot because of wave actions. So it's the shearing of in a turbulent ocean that creates smaller and smaller and smaller pieces that then get biofiled by organisms living on it, and then they sink down. So the waves are actually an integral part of understanding how plastic moves to the ocean floor, and well, SKIM again does something of that.
Thank you. Okay, thank you very much for your time, and I think Wolfram, you can take over. Let's go, Meg.